So basically, I have done for all my research work is to apply numerical models, link them with the data, in particular real-time data, and then provide the end users with the outputs of that work. And that can be very limiting in the sense that if you get a report, you cannot go beyond what is written there. So I started linking my work with IT tools, taking advantage of the information technology division. And what I'm going to present today is basically what we have been creating now to make our end users closer to our work and for them to be able to experiment, test new approaches, and get some ideas that they can then discuss with us and do our consultancy work. So the first thing that I'm going to say, because I think I'm addressing a platform on many modelers, is that these tools are not supposed to substitute your work. They are supposed to help you convey your message and help integrate the end users into common projects that bring benefits to all. And this is usually quite a concern, whether we talk about on-demand modeling tools that appear to substitute your work, but they don't. They help end users to understand your work better. So I hope I'm able to convince you during this presentation of this. The work that we have been doing is mostly related with the coastal environments, mostly due to my background, but we are now evolving towards other water domains, and I'll talk a bit also in my talk about that. There are a number of names here, including João Fernandes, that is on the screen, related to a common project where we started to link our coastal work to the river domains. So this is a very quick outline of my talk. I'll start a little bit by remembering what I mean by forecast in this context, share some motivation on why we are working on this, and then putting our work in the context of a very important initiative that is undergoing from the oceans to the freshwater domains, which is digital twins. So our work is targeted at contributing to coastal digital twins. I'll then talk a little bit about OPENCoastS, what it is, what it does in general, and then go over the several features of OPENCoastS and what you can do in each of them. Because OPENCoastS is a web interface, there's a lot of things going on in the background. So I'll talk about the framework that we have developed to include all types of modeling and forecasting works within the water domains. And I'll talk a little bit about that. Then, as I said before, we are starting to go beyond the coastal domains, and I'll talk a little bit what we have done with João in a European project to integrate river dynamic models in these concepts. So very quickly, what I mean by forecast systems is short-term predictions of the water dynamics for the next few days. So a little bit like the weather predictions that you get in your mobile. Here we need to have forcings at our boundaries to calculate through the prediction simulations what is going to happen in our water domain in the next days. Then we have all the IT working of post-processing, archiving, and providing visual products for the end users. Finally, because I don't believe in any forecast systems that cannot be validated by real-time data, we have the linkage with the real-time data sources and the production of the model data comparisons. So what are forecast systems based on? They're based on typically high accuracy process-based models, although we are starting to include hybrid modeling and AI modelings in the process. These tools require, like I said, continuous validation of real-time data. And one aspect of forecast systems that most of the time people don't think about is that if you archive all the predictions from real-time forecast systems, you end up having a very complete, very broad database of information on your system of interest. And these are the good news. Then the difficulties here start that they require the availability computer resources to do the runs every day. And these runs are done on an automatic way. So you need the computer resources to be automatically linked with the tools that create the forecasts every day. At the same time, this is a chain of computations. You need to have very robust, very reliable, and also very accurate modeling tools, because we cannot use modeling tools that are very sensitive and may blow up, because that will break the chain and your forecast will disappear. Finally, typically, in the past, most of these systems are implemented on a case-by-case way, driven by end users' needs. Like we have a type of estuary forecast system, but that's a very static forecast system. So every time we get a new version of the model, updating all of this requires a lot of resources. So, sorry for the background noise. So why are we doing this, and why is LNEC concerned with this type of tools? Some of our work has to do with supporting our end users to anticipate any hazardous events, and also to provide information so that they can direct emergency actions in a very efficient way. So forecast systems can be very good tools for this. At the same time, they are very, very useful tools for daily tasks, like planning an intervention in a port, or planning a dredging intervention, planning recreation events like regattas and things like this. So it is a tool that not only works for emergency events, other events, but it's also useful every day. At the same time, given the capacity to build long-term databases of information, you can also use forecast systems to support risk management and addressing conflicting uses in coastal areas. In the new approach to the coastal management, we are now looking at integrated ways to provide all the knowledge from the coastal areas, looking from the ocean to the coast. And sorry for the noise, we are next to the airport. And these efforts, called digital twins, are starting to occur in the ocean community and also in the atmospheric community. And we are now starting to downscale them to the coast. And these systems, they integrate models, forecast system, data analysis, and putting all of them together in the service provisioning view. So our vision to address this new challenge at LNEC, and I'm not going to all the details in these figures, is basically to put together all the tools that we have, starting with the data in the right, and then going to our modeling tools and to integrate them into frameworks that can provide the automatic services, and then making them visible and public through services like OPENCoastS that we are going to talk about today, and also other types of services like WIFF that handles remote sensing information. And we hope with that to be able to create products that are used for our clients, managers, companies, researchers, general public, and at the same time to contribute to long-term international initiatives like the UN Decade of Ocean Science and Destination Earth. Oh, one very important aspect that I forgot to say is all of this is only possible with the availability of high-performance computing resources, and for that we are linked with the OSC and the EuroCC providers. Okay, so what can we do of new that traditional forecast systems cannot do? Like I said before, we don't have the human resources to build independent, static forecast systems for all the systems in the coastal system in the world. So the solution to that is look at tools that can be applied in a very efficient way in any coastal system. And by doing this, we are able to get high-resolution information in space and time. We are able to address the what-if scenarios, the climate change scenarios, and other types of local concerns in a very efficient way. And at the same time, by creating these tools, we provide the opportunity to share coastal knowledge with anyone, to provide people with tools to test and experiment before acting or before building, and at the same time to have a tool that can be used for education of young people. Again, we looked at this in the concept of on-demand forecasting as a service. So through a simple to use, user-friendly web interface that does not require people to go command line, does not require the need to know Linux or programming Python, anything. So making this type of knowledge available to everyone. And in that context, we developed OPENCoastS, which basically centralizes all the development, the execution, and the maintenance of forecast systems. So what does OPENCoastS do? So it makes the implementation of forecasts fast and easy. The user is able to select the location of the forecast through a web browser interface. This is quite flexible in the sense that the user can select the forcings to be applied at the boundaries, at the atmospheric part, etc. The process to be solved, so we can be as simple as a barotropic run or as complex as a 3D baroclinic wave and current interaction run, and adding water quality. The user is also able to some extent to play with model parameters, so it can be also interesting from a research point of view, and by this way to give confidence to what people are actually simulating. We have a lot of processes available. You see the list on the screen, and also we are started to working with water quality, starting with less complex problems. We don't have sediments and erosion and accretion being solved at the same time. This is one of the things that we are interested in. From an IT point of view, but I don't want to bother you too much with this. We have built an IT architecture, given our team of computer scientists, that allows this work to be able to grow in the future to additional processes, new models, new processing tools, new water domains. And like I said before, we are supported by the EOSC infrastructure, and we use the EOSC core services to access in an easy way the computational resources. Okay, going a little bit into the processes and what OPENCoastS does. So it generates daily forecasts for a number of variables for the reason of interest for 48 hours. It is organized around 4 main blocks that I will be talking a little bit about in the next slides. The configuration wizard, the forecast and manager, a simple viewer that is not as powerful as a GIS, but does provide some visualization to help users decide if that forecast is okay or if they want to do something new. And at the same time being able to download the results and the input files so the advanced users can go and do their own work in their tools of selection. We are based on numerical simulations of relevant physical processes and some of the biogeochemical processes. OPENCoastS is supported by the modeling suite SCISM. SCISM is an international effort using unstructured triangle grids. So we are able to resolve well cross-scale representations, and in the context of your group, SCISM is often used for compound flooding in a very efficient way, both efficient in terms of representation of the important scales and computationally very, very efficient. As I said before, one thing I forgot. The newest part of OPENCoastS is grid generation. So today, a user can start with nothing at all and to be able to do all the work, all the modeling work inside OPENCoastS. Like I said before, I don't believe in forecast that has no data to be checked with. So we have implemented in an automatic way, to be selected by the user, of course, automatic comparisons with data from LNEC, and also the capacity for the inundation studies to compare with the processing of Sentinel-2 images using another service, the WARSIC remote sensing service, to get the land-water interface at each Sentinel image in the system of interest. So just a very quick, this slide has a lot of images. I'll try to make it as simple as possible. So what you see in the top, this is the configuration of the system. So the part of OPENCoastS where you build your forecast system. It has several steps addressing each of the concerns in a numerical study. So we start by selecting the model, what we want to do, 2D, 3D, baroclinic flow, with or without waves, with or without water quality. Then we select our domain, so the user uploads the grid of the domain with the bathymetry already interpolated. This grid can be produced also inside OPENCoastS and then uploaded here to produce the forecast. We have a number of boundary and surface conditions to propose to our users, and these are all available through drop-downs, so people don't have to know links, define anything, just select among the options that are proposed. And we have ocean boundary conditions, predictions for the atmospheric values, wave predictions, and for the river part, we have the possibility of people putting a climatology for the system of interest, either through an annual value or through a monthly value. The possibility also to provide a link to a river forecast system produced outside OPENCoastS that provides the boundary conditions every day. Then we have also the comparison of the data that I have already talked about. All of this is very simple in the sense that is answering questions and going step by step. We try to encapsulate the knowledge of our coastal division team here. So the user is provided with help in all steps, and also when he has to select like parameters for model, we have predefined parameter files for each type of run that encapsulates the best knowledge from our colleagues. So to try to help the least proficient users to be able in the end to get a forecast that is meaningful and has a reasonable level of accuracy. Then we have the second pillar, which is the forecast manager. So what you see on the screen is a list of my deployments. And here we can do a number of things like knowing the status of the deployment, starting and stopping deployments, cloning a deployment, for instance, to do a parameter analysis, and kill a deployment if it's not producing anything valuable and it's just generating data that no one needs. So this helps our users, in particular our users with many deployments, to be able to manage what they are doing and the disk space they are occupying. Okay, the last pillar on the forecast production is the viewer. Like I said, it's something very simple. We have a list of deployments. We select the variable to see. For the 3D runs, the vertical level we want to see. We can get, by clicking on the screen, time series that are created on the fly. And we also have the possibility to do time series that include all the time steps of output of the model. Here in the viewer, you can only interpolate between the results from the 1 hour outputs. Here we are also able to see the comparison, the inundation comparison with the processing of Sentinel-2 images, if we have defined previously in the configurator that we want to do this comparison. Okay, the most recent addition to OpenCoast, and this was given to the fact that most of our users, and we do a lot of training events, complained that creating an unstructured grid was very difficult. Then we provided some additional classes to build the grid, but that was not enough. And building a good unstructured grid is really a complex task. So we created a mesh generator inside OpenCoast. As you can see, the figure is one of the options now between the several pillars. And at the same time, we are able to store that grid and then use it in the configuration system. This work was done in collaboration with NOAA, with the coastal division of NOAA, and basically we integrated the OCS mesh grid generator, a very agile and very complete grid generator, and put it in the OpenCoastS platform. For the grid generation, the principle is the same. You have here in the figure now the steps for the grid generation, and it basically covers all steps, starting from the definition of the domain down to a generation and downloading of both the horizontal mesh and the vertical mesh. And this is done for Schism grid format, but that format is shared with many other models like AppServe, for instance. What you have here in the figure is a screen capture of several of the steps. So in the first one, we define our domain by creating straight lines or curved lines to define where we want the domain. Then we define a lot of things related with mesh resolution, and there are a lot of options there. Multiple criteria to define different resolutions in different parts of the domain. And then the OCS mesh generates the grid. We are able to get the symmetry from a number of sources, so it automatically interpolates the symmetry. And this interpolation can be done with a combination of several international providers and also with the local bathymetry that the user can upload. And then we go down the line, and for the 3D runs, we are able to generate a vertical mesh also. At the end of the day, we are also able to optimize the quality of the grid, so making the results of our model best using optimizers like NiceGrid. Now, I've been talking about interfaces and nice things, but behind the curtain, there are very complex IT frameworks that make all of this possible. And we started by creating this framework, the WIFF framework, and it is built in a way that is configurable to set up the deployments the user wants. It is basically a group of tasks that are common to all modeling processes. And by combining these several models, we are able to build a very complex deployment. So what you see in the image in the top is basically the general concepts. I didn't go into the details. You have modules for getting boundary conditions, modules for conversion of formats from those boundary conditions to the model boundary condition file, and everything that we need to get to our purpose. In the image of in the bottom, you see how this framework can then be combining the pieces to do very complex simulations. And what you see here is an example for urban inundation forecast. That is WIFF. It's not part of OpenCoastS. OpenCoastS only deals with the coastal part. But you can see that taking this modular approach, we can go as far as we want. Okay. Again, we need a lot of computational resources to make this happen, and we are automatically linked with the OSCE computational resources through the INCD node. Okay. Before I stop, I just want to talk a little bit about the work that we have started to do with our colleagues from the River Division. João Fernandes in particular, as part of a river inundation project. We started by creating the integration of coastal and river models to deal with the flash flood events. And what you see in the figure is basically our conceptual approach. So we have a lot of sensors in the field. We are developing AI models to represent and do the predictions for the sensors. And we combine these with the numerical model approach using HMS and ECRAS with the AI trained models to be able to handle flash floods. This is still an ongoing work. What we have done so far is integrate HMS in WIFF. So it's part of our capacity to do predictions, not inside OpenCoast. So basically this is a combination of forecast, process-based and database modeling to create hybrid models. And we hope in the near future to provide hybrid model predictions and to include the ECAS part in WIFF also. So some directions for what we are going to do next. So basically we were able to establish that we can do relocatable forecast systems and they can be easily used by everyone. These tools are reliable, flexible and quite accurate, depending of course on the input grid that we put there. We are hoping to, in the future, to be able to add new features, new processes, new water domains, and do a better integration between these water domains. So I would like to work from the ocean to the hydrographic basin. As far as river dynamics is concerned, we are starting to integrate it in WIFF, and we hope that we'll be able to create a service for like OpenCoast, but now directed either as freshwater or freshwater to coastal domains. At the same time, integrate all of this work can be interesting, but we cannot work isolatedly. So we are looking into integration with the international initiatives like the European Digital Twin of the Ocean, Destination Earth, and other initiatives to be able to put our work in the hands of everyone. And I'll finish by telling you that all of this is open access. Open access to service, you have the link on the screen. Open access the code, all of the code behind the OpenCoast is available. And we also have a dissemination page that I invite you all to check, where we have the user manual, training material from the several training events and the publications, of course. And that's all I have for you. Thank you so much for your attention.
Okay, thank you. Thank you, Anabela, for this nice presentation. We are a little bit ahead of the schedule, but I think we can open a small Q&A period, so just 2 or 3 questions. I'm sure that Anabela is glad to. Can you stay with us a few more minutes?
Sure.
Okay. So I saw already one question in the chat. If someone, so George, I think you can ask your question.
Thank you. Thanks a lot. Thank you, Anabela, for the presentation. Really insightful. My question is, can this be already applicable to other places like Pacific Islands? And if so, what do you think would be needed to adapt it there? I'm thinking in Portugal, for instance, or other islands there.
Okay. You can apply, I didn't say it, my mistake. You can apply it anywhere in the world. The only limitation right now is the wave part, that we need to have a forcing for the boundaries for waves. And in order to have a good quality circulation, we need to have wave spectra at the boundary. And right now there are no global provider of wave spectra. So we basically have our own wave prediction engine that provides predictions in the North Atlantic. So you can use everything in OpenCoast except for your island, except for the wave part.
And for the wave part, the only thing that I would have to do is to include the wave spectra that I can take from satellites, from synthetic aperture radar, maybe.
Yeah, if you provide us with a wave spectra predictions that we can integrate in OPENCoastS, then you'll be able to do the simulations. Yes, we need to intervene in the sense that we need to put that provider as an option. But if it can be arranged, we'll be more than interested.
Thank you.
Yeah, and I can add one thing I don't know if Anabela said. So the division of Anabela and the coastal division here provide a lot of small training courses during the year. So if you are interested, you can just check with her, and I'm sure, right, Anabela? It's
yes.
So I think it's hands-on, and you can try to use it. I don't know if there's any other question. Maybe we can skip, and I'm sure Anabela will be glad to answer by email or something if someone has further questions. Okay. Back to you. Anabela.
I was just saying that I forgot to put my email here, but the organizers can share my email with the participants. Okay, along with the slides. I sent along the slides before the talk. Okay. Well, thank you for the opportunity, and it was a pleasure to meet you all.